All right, guys, so this is part 2 here. So we're going to have a look at more specific examples here in terms of specific functions that we could actually create the sketches for of these graphs, right? What I find uh, great about these is that we're able to use this notion of the derivative and identifying critical points, and then being able to produce a pretty accurate depiction of what this graph looks like, right? So I'd say here, I don't know, this could be always something that you guys draw out in terms of helping you produce these graphs, right? So I'd say the first thing I would probably do is derive this thing. You know that we're looking for the local max and local mins, right? And so I would say right off the bat, I'd say let's derive this set it equal to 0 and find where those minimum or maximum values are, right? So I'd say, okay, well, let's go f prime of x is going to equal 3x. This is just going to be the power laws, right? Minus 3x squared minus 3. And then we know for maximum and minimum values, we're going to set f prime of x equal to 0. Right? And so 3x squared minus 3 is going to equal 0. And then we're going to just solve, right? So 3x squared is equal to 3. X squared is going to equal 3 divided by 3, which is going to equal 1. And so x is going to equal plus minus 1, right? Square root of 1, which is 1, right? So you have two values. So we're going to look at the values around these two critical points, right? X equals 1 and x equals negative 1, right? So I'm just going to plot those into, at least these identify the points of the graph at where we're mainly interested in, right? So I'd say, okay, well, why don't we check just on the left side of negative 1, so let's say at negative 2, and then we'll say, okay, at negative 1, and then we're going to check on the right side of negative 1, and then we'll go 1, and then we'll go 2, right? And so these are going to be basically like our intervals, right? So everything from everything left of negative 2, so x is less than negative 2, and then what happens here, well, we know what happens here, right? It's no secret. That's going to be a min or max, right? It's going to be a critical point. We're going to use the graph to help us find out which one. And we also know down here that something special is going on, okay? So we know at those points, right? If we were to plug in these points into the original function, right? So we know this is all we're going to do, right? We're going to take these values of x. We're going to check what they are, what their values are in each of the two functions, right? So I'm going to check what the values are in f of x, and I can create a bunch of points. And then I can also, the only thing I'm really interested in purposes of I don't care about the numerical value of the derivative. I really only care about whether or not that derivative is positive or negative. Okay, so if I plug in the values and find out whether or not the derivative is positive or negative, that's going to tell me, how to sketch this graph. Okay, so what we're going to do though is we're going to try and create a mapping of points here in the f of x column. Okay, and so when you do that, when you plug these points in, you're going to get a mapping basically of where everything is. When you were to plug in negative 2 there, you would get 0. All right, so like an x-intercept. And then we're going to see if I were to plug in, I'll do this whole column here, okay? If I plug in negative 1, I would get 4. And for 0, I would get 2. And for 1, I'd get 0. And for 2, I'd get 4. Okay, and then if we were to do the same thing for the derivative function, right, over here, if I were to change the color or something, right, so if I were to plug in these values of x, I get the values, right? Now specifically, you don't care about them numerically. The numerics would just tell you how steep or how, not steep, I guess, or how shallow the actual slope of the graph is at that particular point, which is going to change, right? The slope is, for a cubic function is going to have a whole bunch of different slopes. So that's not, the numerical value doesn't necessarily help you here, but being able to identify positive or negative does. Okay, so for that particular value, for -2, we're going to see that if I were to plug -2 into our derivative function, we're going to see that it comes out to be positive. So we know that along that interval, everywhere less than -2, the slope is going to be positive, right? And then we're going to check another one. Something happens at the here, right? Something special happens. We know that there's a max or min, right? Well, turns out that we're going to get a 0 for the derivative, which means something, which we'll identify after, which is the whole point of why we did this. And then we said, okay, well, what happens on the other side of -1, right? Does it continue to increase, or does it turn around and start decreasing? Well, when you plug in x equals 0 into the derivative function, you're going to see that you get a value of -3 specifically, so we know that it's going to be negative. So if I'm increasing, and then I turn around and go negative, right, that must make this a maximum, right? Then we keep going. Okay, well, we know that the slope here is going to be 0, right? Is it a max or min? I don't know. We'll find out in a second. Let's check this interval here, right? If I were to plug in 2 into this equation, right, the derivative equation, this one, I'm going to see that this comes out to be positive, right? So again, there's a critical point here, but this time I'm going from decreasing back up to increasing. So I get a minimum. Okay, now you can plot these points, sure, right? You could say, okay, well, here's -2. We had an x-intercept at -2, right? So right here. And then up at -1 and 4, we had a point. And we knew that that was going to be a maximum, right? And then 2 and 0, and then 1 and 0, and then we had one final one at 2 and 4. There we go. Okay, so we can produce our graph now. Comes up. Okay, I suppose we can always do this, right? No matter what, we can always create a table of values and create points, right? At the end of the day, though, it's nice to know that the derivatives are reinforcing the shapes of the graphs that we see, right? They fit the points, the derivatives, right? So we know that along the interval of -1, between x equals -1 and x equals 1, we know that that graph is decreasing, right? It tells us that. So between these two, between here, we know that the graph is decreasing. We can see that, right, in the points. So that's what this is doing. It's creating a mapping of what's going on, right? Keeping everything in check too, okay? So I guess you could create one final statement here and state that the critical points are -1 and 4, which would be a local max, and 1 and 0 would be a local minimum. Okay, so that's that, guys. Okay, so we're gonna just, I don't know, do a couple more examples here. Might not necessarily do, well, some of these later ones are a little bit shorter. Okay, so we'll try this one next. Okay, again, same thing. I would follow the same idea here, right? So we're gonna take a look at, okay, well, I'm interested in where is this graph gonna like bounce around, flip back and forth, right? So let's say we're gonna find the derivative, right? Well, taking the derivative of this, we're gonna get 2 times 1 minus x squared, but then I have to multiply by the derivative of the inside. So we're gonna multiply by -2x, right? And so f prime of x is gonna equal -4x times 1 minus x squared. Okay, so for any of the critical points, and remember, this is we would have no idea. Like, keep in mind here, I know up here, like I said, we could do this with any graph, right? Like in terms of plotting in x values and finding out what y values are. That's nothing new. But what is new is that being able to correctly identify which points to actually plug in. Like, where do we even care about this graph, right? That's what the derivative is doing for us, right? We're looking for where these critical points are, right? So for the critical points, right, like I need to know which x values I actually even care about, right? So for the critical points, we're going to set f prime of x equal to 0, right? And find where the x values are such that the derivative is equal to 0. That's going to narrow down my search, right, as to where the graph is. So negative 4x times 1 minus x squared, that has to equal 0. Okay, well, what's going to make this work? Well, x could equal 0 right off the bat. That's kind of like what we call like a trivial solution. We know that x can equal 0. Or we can get the fact that 1 minus x squared equals 0. And so x squared is equal to 1. And same idea as before, x equals plus minus 1, right? So we have 3 critical points here, right? We know that there's 3 critical points because the power on this function is going to be a quartic function, right? Okay, so if we have a quartic function, I think we should expect to see 3 different kind of critical points, right? 3 points in time where the graph turns and changes direction, right? You guys have some experience looking at stuff like that from grade 12 functions, right? And so this allows us to narrow our search down as to which values of x we care about, right? We have an x equals plus minus 1, and then we have an x equals 0. So let's check everything on the left side. So basically, we could check where the graph is at negative 2, negative 1, 0, 1. Oh, we could even be more specific here on this particular question, actually. Let's say maybe we even check what the graph is doing at, I don't know, negative 0.5. And then we'll go 0. Then we'll go 0.5. And 1 and 2. All right, guys, I'm going to move this over so we have some space. Okay. And then you do the same thing. If we were to plug in some values, right, we can see that if I were to plug in negative 2, I'd get 7. If I plug in negative 1, I get negative 2. And then we can see negative 1. So somewhere in between negative 2 and negative 1 is going to be this value. Same thing here. We could plug in 1. We get negative 2 and 7. Okay, we're mainly using this particular value here to check the derivative. Okay, what is the value of the derivative? I don't really necessarily like. We can connect the line of the function between these 2 points. That's not an issue. Okay, but we want to see what's going on in here, right? Specifically, we picked this point for the derivative purposes only. Okay, so let's check the derivative then. If I were to plug these values into the derivative, I would see if I plugged in negative 2, I would get a negative derivative. And then we already identified that this is going to be 0, right? And if I were to plug in negative 0.5 into the derivative equation, I would get a positive slope or a positive value. Okay, so the function is increasing there. Okay, and then again, there's a 0 because we identified it right off the bat, right? These are from these points here. So we had 3 of them, right? So we just wanted to check. We picked these just to check what the graph was doing in between these 2 0 values, right? We needed a value to tell us what the slope was, whether we're going to go up or go down, right? And then at 1/2, we're going to see again that we get negative, and then we knew that that was 0, and then we get a positive value here. So we know, at this particular point, we're going from a negative slope to a positive, negative to positive, looks like that. So we know that this is going to be a minimum. And then from here to here, we're going from a positive slope to a negative. that's going to be a max. And then negative to a positive, again, minimum. Okay, so what does this graph look like? Well, we know everything left of -2 is going to have a negative slope, so something like this, right? Everywhere left of -2. So we know one of the points is -2 and 7. So that'd be up here, way up here somewhere. I don't know. And then -1 and -2. Well, that's right here. Okay, so we know that this is going to be a minimum value. So the graph is going to come down here and turn around, right? And then we know, well, okay, again, at -1/2, so somewhere in here, we're going to have a positive slope on this interval somewhere, right? So let's jump over to the next critical point and plot it, 0, -1, right? And then 1, I suppose you guys could probably plot all these critical points first things first, right? To help you. As I'm doing this, I'm like, okay, what's the best way to do this? You could probably plot these 3 critical points, right? And then use the fact, we know we're going to be decreasing on this interval, right? And 2 and 7 is up here again. So it looks like a quartic function, right? We're going to come down. It's going to go through 1. Okay, it looks like everything checks out, right? It looks like, okay, on this, when x is a -1/2 on this interval, somewhere in here, the slope is positive, right? Slope is positive. And then on the interval of here, the slope was negative. Okay, so this allows you to create, I don't know, better pictures, right? Reinforces why the pictures are the way that they are, right? The graphs. Okay, why don't we try? Here, I'll hit pause there. That'll be part 2, and then we'll finish off this lesson, okay?